All right. So hello everyone, and thanks for joining this presentation, and thanks for OLake for organizing such great event. So today I'll be talking about real-time data pipelines, especially distributed stream processing. So yeah, the outline is basically how was stream processing or data processing in general in the near future and how's now and what is actually distributed stream processing, some architectural patterns, and some design ideas and design principles for scaling, and also best practices for distributed stream processing, things to be taken care of and to be considered. And finally, we'll just wrap up with Q&A. Just briefly about me. So I originally had my industrial engineering degree in 2019. And at the same year, I started my master's in data mining. This was kind of my first entrance into data field. Before that, I had couple of scholarships or small kind of internships, but nothing the big. And near the end of my masters, I got my also official data position as a data scientist in a startup company, which was a great opportunity and a bit challenging because despite my title was data scientist, I was the only data person in the whole company. So I was both data engineer, data scientist, data architect, data analyst with no experience. So it was a bit challenging, but also creates the very nice opportunities for learning. And soon after I got my position, I also graduated from data mining, and then I started my PhD in data engineering. This was the time I was actually not 100% aware. Okay, what's are the actual differences between them and everything. So the PhD in data engineering was somewhat a coincidence, but ended up the field that I loved the most. And throughout my PhD, I also continued working as a data scientist mostly, and that's why I recognized that all right, I'm mostly interested in data engineering stuff and everything. So I started to shift into data engineering, and for about last 1.5 year, I'm a data engineer. And yeah, that's I think all about me for now, and about stream processing. In the beginning, all the systems were batch first. So the typical approach was running a scheduled approach, some cron jobs, some ETL pipelines, sometimes once a day, once a couple day, or even the hourly jobs were not that common, if I can recall. So data would be pulled from various systems, then transformed and loaded into mostly databases for reporting and analysis. As the applications evolved, after maybe 2000, 2010, the volume of data started to increase rapidly, with the internet and all the technological developments. We started to see a lot of event-based systems, where systems generate and emit events, such as user clicks, transactions, or some logs, device readings, everything. So there are still a lot of pipelines that micro batch, they are not actually real time, but they are a bit different than the traditional batch jobs because they are running in quite low intervals and they are processing quite a lot of event data, and they aim to just provide, for example, insights within couple of minutes or 10 minutes, very short intervals, almost near real time. And recently, I'd say maybe after 2018 or something, we started to see the shift toward the real streaming systems. So these systems like aim to just process the data as they are generated, immediately after. We are talking from milliseconds of latency rather than minutes. So with the improvements in like cloud like services, and also recently like IoT like devices, it's right now possible to process like millions of data within a like couple seconds. So that we started to see this near real time approach where we can track like everything in like seconds of intervals, like which is sometimes very crucial for like banking operations. It might be some like fraud detection systems that should be immediately logged, or like some surveillance cameras that should like ring the bell immediately if it detects something suspicious. So streaming now have like couple of use cases, and like it's like mostly still used like analytics dashboards. So there may be like business users, like they don't want to wait hours for metrics. They expect live dashboards, like how metrics evolves, trends. Even sometimes there's like live like machine learning, like algorithms going through analytics and provide them some like real-time estimates. And like as I mentioned, like fraud and animal detection, it's very crucial in industries like e-commerce and banking, and like to detect like suspicious activities or harmful activities real time, like stream processing is somehow are on the way. And on the other end, there is like applications or like use cases that user immediately face with some kind of functionality that is like fed by data. So many apps today offer like live dashboards or personalized recommendation, instant feedback, like just after you click something, it like generates a recommendation for you, or it changes your feed and everything. And another interesting use case is like machine learning feature generation. So like many machine learning models need fresh data, and like freshness here is like very small granularity. So instead of relying on like batch generated features, there are some pipelines that gets like real-time data, get trained on them, update their like model, and go with that. So it's like a machine's learning while like proceeding. And like most like one of the hot topics, and the one that I also like worked on my PhD, is like IoT and sensors and edge computing. It's like the smart devices and like sensors, they are everywhere, and right now we are trying to like do some kind of like continuous like data processing in the place where data is generated. So this is also like one of the biggest use cases and one of the promising use cases actually. So on the other end, there is like distributed stream processing. So like what is, how is it different than the like stream processing like in general? So the distributed stream processing is that the data is still processed continuously. However, like we kind of like divide our operations into small operators in like small and like easily processable chunks, that we can divide these tasks within multiple devices or like CPUs, so that we can process very small operation in a distributed manner continuously, so that instead of performing, for example, a single operation in a device for 2 seconds, while dividing this way, in each device, we may perform an operation that will cost us 2 milliseconds. And overall, instead of like 2 seconds, we'll have like just 10 milliseconds, and we'll process the same data in chunks. So each operator may like do very little operations like map, filter, join, like the known like data operations, or even a bit like big ones like linear regression, or they may do some like decision tree model like estimations, everything. The main aim here is that having as low latency as possible and scaling as much as possible, so that the responsiveness kind of like increases. It can have like multiple sources. There may be like multiple sensors all around. Like thinking about a traditional edge computing like framework, we kind of have like hundreds of sensors like continuously kind of like pumping some data inside our system, and we have maybe like hundreds of other like IoT devices all around our network that's processing this data continuously, and like at the end sending this data to a sink. It can be data lake, it can be a database, like something that we can just make use of this data. So there are some types of processing in the like structure that I mentioned here. There are like a lot of challenge going on, and like the processing can be either at most once. So in here, each event can be like processed once. This is very fast, like you just send the data and that's it. But if in the middle there's something fails and something happens, you kind of lost your data. So yeah, in exchange of like fast like response, you kind of risk it. And on the other hand, we have at least once. This is like commonly used like approach, actually. Like this kind of have every event will be processed, but there may be some ones, for example, duplicates, because this will try to process a single data until it ensures that it's processed. So it can do some health checks and detect that, okay, if this data is like processed, if it doesn't have the result yet, it will send it again. So this is like also in exchange that you have more reliability, but you risk duplicates and also you kind of lose performance. Exactly once on the end, this is the gold standard. Like all of us, we want to do that. Like each event is processed once with no loss or duplication. This is the standard that want to ensure that the data is only and only once processed. So, but to achieve that, sometimes it may be very costly, and there may be a lot of like performance trade-offs in the meantime. And like today, different frameworks and applications choose different guarantees. And like this is kind of like one of the decisions as a like data engineers we want to make. For example, one of the common ones is AWS Kinesis, for example, Firehose. It have at least one. So if you don't manage it properly, you may end up with a lot of duplicate events, or you'll need to do, for example, some kind of deduplication jobs on top of that, such kind of trade-offs. So one of the like first things to like consider in the like stream processing systems is like architectural patterns. Like there are some specific fundamental patterns that we need to consider. For example, the first one is between like stateless and stateful processing. So in stateless processing, like we mean each event is processed independently, so that the processor here, like the flow, like event comes, the function kind of processes it and sends the output. The processor doesn't need to remember anything between events. Like the simple example would be like a filtering, for example, to checking that, okay, if this number is higher than 10 or not. If it's higher, it will send it. If it's not, it will drop it. That's it. But in stateful processing, the system maintains a state across events. So the idea is that the event comes, the event is processed, or like there may be also like state involves before function as well. So the event is kind of like executed like by keeping some of the, for example, previous executions also, which like we refer as state. Then we have new output, and using the new output, we update states. So the example here would be like tracking the running count of events, for example. There can be a like aggregate metric over some time window. So if our time window is like 5 minutes, we are kind of interested in the like last 5 minutes. So we need to keep it state. So stateful processing is a like very like strong concept. However, it adds some complexity. So we'll need to manage it, we'll need to scale it, and we need to have a mechanism to like handle like failures if something stops. And another like concept in like is like time, like the definition of times in stream processing. For example, we have both event time and processing time. Event time is when the event is actually happened. For example, when a user clicked a button. So this is a, like kind of like timestamp in like the transactional databases. It's very useful, but for measuring the like performance, if it's something to be relied on, there will be some like huge mistakes because there is like gaps in between the like event is generated and even event is actually emitted in this like system. So processing time on the other hand, like it's when the event is processed by the system, so which could be also delayed by like network lags and retrieve and failures. So that within this like our stream processing architecture, we'll need to maintain this time structure and make use of like event time and processing time as like correctly as possible to have like meaningful metrics. Like most of the frameworks right now provide their own like calculations which are like pretty much handling those for us, but still it's somehow like fundamental to be aware of. Land like streams are often out of order, so event can arrive late, and definitely they will, their order may change, there may be delayed packets and everything. So good systems should be somehow like properly. And there are some like common architecture patterns, like they are like used for a variety of like scales of like projects and teams like that, and like we can still often see them. The like the most common one is like and having an event source, like there is like often a message queue like Kafka, and act as a buffer which like feeds the system with the data and manages the like incoming queue, and in case of failures it kind of provides also some like retrying and like it provides data again. And in like the middle we have like stream processor, which is like frameworks that provide some kind of like real-time data processing, and they also able to handle the queuing in processing themselves. Like this is where we apply the business logic, this is where we do all the computation, filtering, transformation, everything. Like currently apache flink is somehow like the de facto here. It used to be storm, but storm started to be old, and like with community support apache flink I think took over the market. And then we'll have our sinks, like this is the results, like the place that the results are pushed. Like they can be databases, data lakes, even there can be directly dashboards. Like in the flow I put them as a separate, but dashboard can be minutes there. But the best practice is to usually store the data in somewhere, then feed the system to be most reliable. So yeah, like the main structure is like that, and distributed stream processing is like the ones that we thought. However, in the scale, there are like different, for example, concepts to be like considered, like partitioning and parallelism. So that to scale stream processing, we need to distribute the work across multiple devices and the operators. We mean like this is done through partitioning, actually, like splitting the stream into smaller pieces that can be processed independently. But by time to time, we may also like re-aggregate them to make use of them, or there may be some ordering. So this is somehow a challenging step while designing streams, depending on the use case. And ideally, the more partitions we have, the more parallelism the system can achieve, so that it will use more resource and it will have higher performances. And like the key idea here is that like the choosing the right partitioning strategy. For example, we can use key by ID, key by category, so that each event, for example, can go to different processor depending on their category. However, there can be CQ and there may be like some imbalances that may also cause some like performance issues if it's not handled properly. And another thing is that back pressures, they are like the most painful stuff that most systems are dealing. Back pressure is when a part of the pipeline can't keep up and it kind of slows down until the source. So that for assume that we have this kind of like flow going on and we just have a like bottleneck just after our orange node. That means that either this orange node sends the data a bit like slowly, or the purple one is unable to just process it as like fast as the other one. So this kind of creates a queue immediately before the like orange one. And having queue here kind of also creates another queue in the backward. So this goes until the source where the data got stacked up. There may be huge traffic spikes. There may be some like nodes failing if they cannot handle, like the worst thing can be that like there can be out of memory error and the device may like shut down. And like modern systems like trying to handle this back pressure through buffering, some like throttling the input or auto scaling, for example. If they detect a bottleneck here, they try to immediately create a parallel instance for this purple one to support it so that they can handle the pressure together. But they are also coming like with cost, all of them, both auto scaling and the NIF device cost. So another issue is that fault tolerance, so that like systems must handle node failures. This node can be like immediately fail in the flow, and all the like the data inside its queue, the processing one, the unfinished one, will need to be able to like save this somehow. We'll need to like recover that one. There are different strategies. One of the like common one is checkpointing. So some kind of like brain node gets checkpoint of the whole system with some intervals, assume like every 2 minutes. So in case of such failure, it recovers from there. So there are actually some trade-offs with like checkpointing performance and also interval. But yeah, like with real time, things always fail. So we need some kind of reprocessing for event streams when needed. And with this like left structure, it's actually a bit easy to think that, all right, like this shouldn't be that hard. But with the like actual flow we see in the real scheduling and the real devices, like the flow is actually a bit more complicated and a bit more wrangled, so that the right hand side is actually as like scheduled version of the left hand side topology, so that each nodes are assigned to a different device, so that they will be like getting, for example, the inputs from some output like some sensors or something, and they will be sending through the device and they will share their outputs according to this topology, so that there may be some uneven loads. Some operators may slow down the others, and they should be able to handle the window operations. And if even the devices are heterogeneous, it may also cause some more issues because some device will be slower than others. So even if they process the identical like operators, there will be performance differences, everything. So scheduling is also like another challenge. Right now, all the like new frameworks kind of provide some kind of like smart scheduling approach, but still time to time, like the engineers need to like implement their own like scheduling approach to like play around them if they are also familiar with the operators going inside. But it's usually better. And like some best practices for distributed stream processing, for example, There are common architectures for variety of like sizes and data maturity, like assuming that like, a small scale or early stage like data ecosystem can be like handled by the simplest architecture, like using a message broker, such as like it can be Kafka, it can be RabbitMQ, it can be Red Panda, and it can like simply combine with a Flink in a standalone mode. So you can have your like virtual machine, and you can like host your Flink like nodes on top of that and process the data. And you can even run them in locally in Docker Compose, depending on the scale. Like sometimes teams even use like Spark like streaming framework instead of Flink. And yeah, like the main advantage here is that like it's very easy to get started, like no heavy infrastructure needed. The downside is scalability is very limited because you are running standalone, and operational complexity is very high because you kind of manage everything by yourself. On top of that, like for medium scales, this is like more common to like requiring some kind of more robust setups, like some combination with managed services. So like for example, a message broker, then a like Flink on Kubernetes, or like managed Kafka, or like some kind of like platform support. So these kind of like scales should somehow a mechanism to like have like be scaling it, like preferably auto scaling. If something kind of bottlenecks, it maybe like handle that. And but it's more expensive, and also it requires some experienced engineers to manage the Kubernetes clusters and like the managed services. And in the large scale, like enterprise levels, like the most major organizations standard up fully managed systems like cloud native services, for example AWS Kinesis plus Apache Flink, or like Azure's event hubs plus Flink. Kind of the thing is that operational overhead here is very low, but it kind of have vendor lock-in. It can be extremely expensive. It's not designed uh, pretty well, and there may be some like flexibility limits because you kind of like delegate your uh, like operations to the service. So there is also like some like common best practices around like some of the like fundamentals, for example in data modeling. So it's always good to using a clear event schema, so like to know that what event is capturing and like how its schema like exists, and also how to like have its like kind of like lineage, how the schema evolves, like how was it, how it changed now and everything. So some kind of like observability here is kind of important. It's always useful to keeping metadata in streaming systems. It's so hard to track back if something's like breaks in all of a sudden, because the data continues to flows. It's not like we just query database and everything. Like to handle such metadata and versioning is very important. And in terms of processing, like event time processing with watermarks instead of processing time is kind of always better. This gives more accurate aggregation in the face of delays, so that you kind of like watermark your events to keep track of like their like lineage. And there should be always a mechanism to handle late arriving events, so that if you strictly run like some kind of like time-based operations, some late arriving events may always be missed. But to handle them, if you for example accept something like all right, accept events that minutes before and everything, it might be also cause some issues. And idempotency, like as like all the other pipelines, it's very important. Like there shouldn't be like duplicate results ideally, because there will be a lot of retries and replies. So which all of them, if idempotency is not handled very well all the time, it will just create duplicates data, like millions of them. And lastly, like scaling, like the partitioning strategy is extremely important. Like continuously monitoring the like consumer lag is very important. So like this is kind of tells us like if our consumers are keeping up, if they can handle the data that we are sending, we may be processing the data amazingly, but it may not be emitted in a proper way. And also the like handling the parallelism. So this is like it can be based on CPU usage and back pressure and everything, but like it's always like this is one of the most important things like in the like scaling part. And like finally, like in production, like some the success of the like system is kind of depending on like having strong observability, because without observability we don't even know like if we are delivering properly. So we want to monitor end-to-end data from the ingestion through the delivery, like through the whole pipeline. For example, for ingestion, there may be some health checks, like for example Kafka have consumer lags, show that like this shows whether your processors are keeping up. For processing, there may be some like operator related metrics, like how many like tuples like executed, what's the average like delay there, or like execution time there, and everything like the queue sizes. And like latency tracking for end-to-end, for example, on average what is the average delivery per each event, for example. And error rates, like how often like events are failing, how often nodes are failing, which ones tend to fail. This is somehow creates like let us design scenarios around them. And also throughput trends, this also show like may really help our like planning, because like throughput is somehow like the output of like dependent on the output of our operators. Some of the operators may be outputting way higher than the others, and knowing that may really like help us designing a better system. So always tracking that and seeing the balance and skills is very important. And like most importantly, like these days almost all the services provided alerts, like when we have a lag spike, when we have a like a fail and everything, when we have unexpectedly increased latency or unexpected rate of events, or like some very high CPU usage and everything, they are all like very good like metrics for us. And yeah, like that's almost all the things that I'd like to share today, and hope you like it. And I think we have some questions, and like we can have also like Q&A on top of that. Let me check that.
Sure. If you want, I can also read out questions for you,
Oh
and
yeah,
we
for
can
sure.
begin, right?
Yeah, for sure.
Okay, great. I mean, first of all, thank you so much for your presentation. It was insightful to me, and actually brought kind of a lot of curiosity. And I'm sure kind of same happened with the audience as well. We have a couple of questions we can tap into. So yes, let's first start with Shubham's question.
Yeah.
Yeah. So he asks, what are the techniques to process data exactly once an ELT from Kafka?
Oh yeah, like processing like uh, data exactly once in ELT from Kafka is kind of like a bit tricky, because the idea of Kafka is actually letting us handling this data like multiple time if it's possible. It keeps like it's like buffers, and if it keeps its cache. But the I think main idea would be like designing a publisher logic there in the network, so that it should keep the event that it gets with some specific unique ID. It keeps there until it ensures that it delivered to the ELT pipeline itself. but this is also costly. Like it requires some of the like checks at the meantime. To be honest, I don't believe like Kafka is like one of the like good like tools for exactly once delivery. Yeah, like even like I really struggle like how I could design such thing to like answer your question. Yeah.
Just a follow up to that question, Hassan.
Yeah.
Uh, like, do you think like Kafka is going to like stay dominant for long because like it is so costly? It becomes so costly eventually. So, what
Yeah.
is your take on that?
Like I think it will definitely be around in the market in like very dominantly for some time because it have some like community support, it have some like good ecosystem and everything. But as you said, it's very costly and it have performance issues,
Mhm.
even like the delivery issue is one. So I believe it will be around for a while. Not, I don't think much long, but for a while for big scale companies because they'll tend to use this managed services, but with more and more greenfield projects where they will try a like ideally better like frameworks. I think yeah, Kafka's I'd expect its popularity to be like continuously decrease until like 2030 or something, the upcoming 5 years.
Yeah.
And from that point it only depends on like the market, the competitors. If they perform well, I think yeah, there we may have like new, definitely new tools that will replace that.
And what are the alternatives that you are seeing in the market, like against Kafka?
Yeah, like there's
And
like for example RabbitMQ is one of them. It's also like one of the other message brokers that's commonly used, but somehow it also have its flaws, so it couldn't find, for example, a how to say like a big of market share because of like the like Kafka's dominance. And there was also like for most of the cloud services, they also have their own like message brokers,
yeah,
but like they also kind of imply some vendor lock-in. So
yeah,
people may not want to use that. So still services that can be used as a standalone or can be supported by standalone service, I think from preference. And right now, to be honest, I think Kafka is like maybe like one of like only one or maybe one like one of the two that serves that, I guess. Like from this I see what peoples are using.
okay, great. Yeah, let's hop on to another question.
Mm.
Uh, we'll take Rohan's question now.
Yeah.
He asks, what is the most common slash suggested way to manage schema in ELT from Kafka?
Hmm. Yeah, like schema management is always a like painful like step. Like in one of the implement, like I to be honest, I don't really sure one like the most common or suggested one, but in one of my like implementations, I had some kind of like my like metadata stored in a data lake. So within some time intervals, I was like using this metadata as my data contract to like kind of validate my schema. And in case of updates, I was performing them. But this is also something costly. I'm not sure if it's even best practice, but yeah, this is something I came across and did once. Yeah. Oh, sorry, Harsha, I cannot hear you. Yeah.
Yeah, I'm so sorry, I was on mute.
Yeah.
Thank you. Another question asked from Shubham. What can
Yeah.
be possible solutions when Kafka is facing back pressure on one of the partitions?
Oh yeah, like this one is I think very common one. So this should be like considered even somehow like redesigning this partition. So this partition may be like spread into like couple. It's like where we like parallel process it, or this can be also like in the other end of Kafka to like let these partitions like processing if we can manage that end, so that it kind of take off some of the like overload from Kafka into the system for like processing. So this may be helpful, but yeah, like in Kafka's and to manage that like this like heavy partitions, there should be like somehow like maybe if it's possible, the best way to be redesigned like partitioning at that end. Yeah.
Great. I hope Shubham you got your answer. Moving on to the next question asked
Yeah.
from Nihar. So yeah, he asks, how can we scale up ingesting application horizontally? Example, data sources Postgres and the ingestion application in Debezium or AWS DMS. I had sudden spike in the insert update actions in my PostgreSQL DB and that issue with Debezium slash DMS.
Yeah. So yeah, there are like usually like one of the options are the like immediately like upscaling the database instance, for example, to handle more. But this, if this is like sudden spike comes and go, it may not be efficient. But for such spikes, there may be somehow like like for example a backup instance in case of spikes that can like support and come and go. But usually these ones are a bit harder in database side. So to be honest, I mostly worked with processing part. Processing part for us, it's a bit easier because we can easily create instances and just kill them like this, so easy. But for database ones, yeah, it's a bit challenging. This should be like the database should be like scaled in a way that it can tolerate almost everything and to some extent the spike. But yeah, there may be some like unavoidable issues.
Hmm.
I don't think there is a solution that will definitely solve that. I don't think it exists.
Okay. Thank you, Nihar. I guess your question has been answered. Okay, moving on to the next question from Dio. When syncing data from Kafka using Flink or other ETL tools, how much of the order of the message matters?
Oh, this is like 100% dependent on the use case. So in some of the like use cases, it may not be as important at all. Like we may not care about that. We may just see that, all right, like did we get this interval, for example. But for some specific use cases, the order might be like important. We may be running some kind of like unique filtering or some like metrics to keep like the or like to consider the event ordering. For example, assuming that we are using some kind of implementation for self-driving cars, assume the order might be important here to detect object around rather than like consider some wide windows. So that yeah, like this is 100% use case dependent, sometimes 0%, sometimes 100%.
Got it. Thank you. Thank you, Hasan. So yes, I have a couple of personal questions and professional questions to ask from you. Uh, would love if you can give insights to the audience present here. So first is I think you have been in data for some years now. So what's changed the most in how companies approach real time data today?
Yeah, like from what I see, for example, I've been in real-time data processing for about 3 to 4 years, I'd say, both in academia and like industry. So I'd see a shift into like less real time, but a bit because like At some point, like all the companies and teams were so hyped around that they think that okay, it will solve everything. We'll have real-time dashboards. Then the like problems started to came, the costs, the like managing such like systems and services, and also like some kind of not suitable use cases. Like, so I think recently companies are more started to be more aware of which use cases really need real-time data processing and which of them not. And they started to like consider this while designing their systems, because throughout like my experience I started to deal less data swamps, for example. At some point with the like increase of data lakes, we started to see data swamps that companies were, for example, tracking all the events, dumping them into data lake, hoping that they'll be using them at some point. But usually you cannot use such data and it's hard to clean. So I'd say that like currently the maybe usage trend is not increasing, but the like use case selections are becoming, I think, more like smarter and more suitable. So definitely there is some like real-time data literacy increasing going on. Yeah. Sorry, Harsha. Like I can hear
Yeah, I'm
you.
so sorry about it.
No worries.
Yeah, thank you. So this is a conclusion question I would like to I like to ask all the speakers. So yes, if you were starting your data engineering career today, what would you focus on learning first, and what would you avoid? Like some of the advice that you would want to give to data engineers today.
Oh yeah, like this is an amazing question, because I like all, like in data field we usually have like different like backgrounds. So I have engineering background. I came from like factories optimizing like machines and like production lines to this data field. And initially I thought like data science, for example, as something software engineering, and I kind of like try to practice coding a lot, which I'm grateful, because currently in data engineering I think one of the like important skill is really like software engineering and best practices. And even if I go back to that date, I do the same and go with. And what would I avoid is definitely studying or trying to learn all the tools in the market rather than getting the fundamentals, like understanding them first, because there are a lot of shiny and like bright tools. Like when we first get into, we like to learn that and that and that. There is a lot of, there is dbt, there is snowflake, there is like a lot of things. And to be honest, probably after like months of work, I learned how these tools work and everything. Then I realized that I have no idea what to do with those tools. So then I get back into like fundamentals and trying started to learn like the core of the like the data. If I had a chance, I definitely avoid like this like meaningless like the like tool oriented or like learning at the beginning. At least after fundamentals, definitely they are so helpful.
Great, great. Thank you so much, Hassan. It has been so much insightful, speaking to you, and uh, like listening to you as well. Thank you so much. And I think we
Yes.
are okay. We have one another question from Manikandan, if we can just take it.
Yeah.
So yeah, how AI will do disruption in data engineering, especially on the structured data.
Well, I'm not sure about like what like disruption like mean there. Like, could you like elaborate on that slightly a bit? Because this seems very interesting question also.
I think, he means to say, AI is kind of like, coming into every sector and every industry, right? So how
Yeah.
is AI going to help data engineers out there, or would want to just come in between the industry? So I
Oh
think
yeah.
that uh,
Yeah.
yeah, unstructured data is taken by LLM, he
Oh
said.
yeah. Yeah. And especially, and in the question, it's especially on the structured data. Yes, so AI definitely changed the way data engineering works slightly a bit. So it provides some support. However, unstructured data in LLMs is somehow still, I think, the most challenging tasks. Like I see people doing PhDs on them, how to handle handle unstructured data and everything. And to be honest, I agree. I also see AI data engineer roles. However, I'm not a big fan of them because data engineering itself is somehow too wide role that I don't know how it can be extended. Maybe it's a role that requires 8, 10 years of experience. That's why I can understand. But in terms of structured data, for example, using LLM tools, it it does provide some support. For example, despite LLMs are not good at SQL, there is a lot of tests around that. Even you can test they may make some silly mistakes time to time. It still provides some helps. It still provides some kind of, if data is structured enough, it can provide some short schemes that you can get from. But in terms of unstructured data, it's, I think, more helpful because it's not easy for us to handle, at least to put into a structured way, process it a bit. It kind of can provide some leads to us, but to be honest, I don't see much of, also definitely it's a helpful stuff, people should learn how to use that, but in data engineering it's not something to be relied on. It can provide some support with programming. It can provide some kind of software engineering best practices, but considering all of the tools in the market is pretty new, there is not enough data to be AIs to be trained on them. So it usually do not provide much of a support from my experience. But for some traditional, or we can say the old legacy stuff, it can be really helpful time to time.
Okay, great. He also says, he's seeing the roles of AI data engineer now. This is somewhat
Ye-
new to me, but yeah, I am not surprised at all.
Yeah, but I to be honest, I'm not fan of such roles. I don't actually can understand. Okay, how would you define responsibilities of an AI engineer? This is something very challenging to me. It would be like a man, with capabilities of 3, 4, I don't know, something like that.
I guess he's typing. But yeah,
Yeah.
I mean, we can have the discussion. Also, I'll take moment to introduce Shubham, our CTO. So Nihar asked this question, right? It's an interesting question, and Hassan also said there is no possible solution on his knowledge right now. But we at OLake are building something similar around it, and I have Shubham here to explain how it does. Nihar, if you are on board still, we can have your answer. So yes, it's for you, Nihar. Shubham, you can take the floor.
Hey, first of all, hey, hi, Hasan. Thanks for the
Hi.
great presentation. I have been a data engineer as well for last almost 8 years, and it's been like hell of a ride when it comes to the real time streaming and like getting the data into the data lakes via Kafka. That's why I asked many questions to you. Maybe you have some new strategy or things around it. But quickly answering Nihar's question. So right now we have a couple of plans around when the spike comes up, when you like add a certain value in some column, like you modify a huge column, or you delete huge amount of data, the CDC spikes. And we have we have in, at least in the current version of OLake, we have parallel processing for the CDC. So if there is a spike, you can actually increase number of threads. So it will read the data from the wall logs or bin logs, and it will send it down the stream in a parallel, to be processed in a parallel way. Like downstream processing can be parallelized, but I don't think walls and bin logs give you that option to process bin logs and walls parallelly. So that's what we have. You can increase the number of threads and increase the speed of the processing if you have like tons of CDC data coming in. As of now, that's one solution. Apart from that, we have heart beating planned as a part of this. So you can check out the community issues. We have a ticket where we are going to implement a heart beating similar to Debezium. And we also have a couple of other things, like this has been raised by a lot of other people as well. So we are planning on like adding a couple of more features for the spikes. But as of now, this is the only tool we have to really try out the project. We are already way faster than other ELT tools. So I think even if there are spikes, if you increase the threads, I don't see, unless until you have like billions of events coming in a spike, we should be able to handle this as a part of the fast ELT.
Okay, great.
Yeah, this is pretty cool to hear, by the way. Like, because the challenge itself is like, it's like very big challenge. I could only imagine that the work behind that to design such framework. It's very interesting.
Thank you.